I'm going to present two ongoing research projects in which virtual reconstruction and analysis form part. The first is on Aztec noise whistles, and the second on the quadruple flutes of Teotihuacan. My fellow colleagues and co-speakers are Sascha Frühholz, Pablo Rodriguez, and Jared Katz. Let's start with the noise whistles. We are particularly interested in the acoustics and psychoacoustics of these tiny instruments. I have here a replica. This is a proper replica of one of these instruments, which you see also in the PowerPoint presentation on the left. The original is stored in the Ethnological Museum, Berlin, and the sound is like this. Noise. This is why they are called noise whistles. The organology of these instruments is quite particular and interesting. These are aerophones, of course, wind instruments belonging to the rare group of so-called free aerophones. So not to the group of conventional wind instruments such as trumpets, flutes, or reed instruments. They are characterized by a particular composition of internal chambers, creating a nonlinear sound, in other words, noise. There has been some research on these instruments. The first reference was published by Julius Kollmann in 1896. But actually, the first speculations about their acoustic functions were only published in the 1970s and the 1990s. And then between 2005 and 2008, me and another colleague, Roberto Velázquez Cabrera, who unfortunately died a couple of years ago, carried out further research, and we proposed kind of refined ideas about their acoustic function. My hypothesis, which was published in several papers, is that these instruments are composed of these several elements. I briefly review them. One is an air duct with constricted passage, which is actually working like a Venturi tube. And Venturi was an Italian researcher who was the first person to describe what happens in such an element. This tube with a constricted passage creates a partial vacuum right after the exit of that passage. B is an hemispherical chamber, which I call a counter-pressure chamber. This is not the principal resonator of this instrument. C is the little part in between these two chambers, which I call a collision or chaos chamber, in which the generated air streams collide and thus produce this noise. And D then is the principal resonator connected to the bell of the instrument. So far, I was not able to actually prove this hypothesis. I'm still working on possibilities to carry out virtual analysis of the acoustic function. And one proposal could be to put these instruments into a virtual 3D wind tunnel, belonging to the fields of aeroacoustics then, and such wind tunnel could simulate the parts in which noise is generated, but also the parts in which the vacuum is generated. Here you see on the left this car, and this mirror here while driving would create this sound, this noise, and the red parts here simulate the noise. And here you see these brown parts simulating the noise of an airplane landing. So something like this could be done, but of course the technology involved is complex and it's also costly. I was in contact with the MIT, and I am in contact with Siemens, and I hope that I can generate cooperation there with these companies. But then also 2 years ago, Sasha and Pablo turned up, and they had an own approach to this problem, and they will show this in a minute on a video. I just will briefly show, because this is just the introduction to this, another possibility how we could let's say visualize what happens in these instruments, and that could be via smoke propagation analysis using ultra-fast photography, demonstrating also the internal airflow and stream interaction. But for this, we would need a fully transparent, clear printed model of this instrument, and that's another technical issue. So now, Alfonsina, please, can you play the first video?
Hello, everybody. My name is Sascha Frühholz. I'm professor for cognitive and affective neuroscience at the University of Zurich. I present work today that I did together with Pablo Rodriguez about the Aztec skull whistles from two perspectives. One perspective is the computational fluid dynamics, and the other one is the psychoacoustic effects of the skull whistles. So in terms of the computational fluid dynamics, we started modeling the airflow within the skull whistles with a more simplified 2D model. This was actually based on typical cross sections that you typically find for the original, but also for replicas of the skull whistle. With a standard composition, you have two spheres that are nested within each other. And actually, what we want to do with the CFD modeling, we want to model the airflow. Once it enters the skull whistles, then it is distributed within the skull whistles, and at a certain point, the air is exiting the skull whistle again. So I quickly show you how this works. This is an example of this 2D computation fluid dynamic modeling within the skull whistle. You see the air, it's entering here. You see it's distributed within the inner sphere and then within the outer sphere. And at one point, the air is leaving the skull whistle again. We do this 2D modeling also with the aim to finally catch the sound that is produced at different parts of the skull whistle. I just play a few example sounds here that we picked up from the skull whistles at different parts. The first sound is actually picked up here at the intersection between the two spheres. It sounds like this. The second sound is catched here from the outer rim of the skull whistle. It sounds like this, and we have another sound. This is probably a clear pitch sound here in the currents, in the eddy currents within the death whistle, the skull whistle. And then finally, we combine all these sounds, and this is actually the sound, how it sounds like when the air is leaving the skull whistle again. It's a mix of all the other sounds. Sounds like this. It's a noisy, high-pitched sound. It's not really satisfying. It doesn't sound very similar to the original sounds of the skull whistles. It sounds similar. It's not perfect. It's not bad, but we're not really satisfied here. So this is why we do now, and this is still work in progress, want to come up with a more realistic 3D model of the skull whistles. So this is why we took replicas that were actually provided by Adje. We took them to a CT machine that you typically find in hospitals. And with this CT machine, actually, we can create 3D models, realistic 3D models of the skull whistles, which you see here. Just rotate them a little bit here. With these 3D models now, and again, I have to say this is work in progress. We're a little bit stuck here because also of the coronavirus. We want to model really the airflow within the skull whistles once it enters the skull whistles, and the distribution also in the second compartment, and also like the sound, how it sounds like once the air is exiting the skull whistle again. The second part of our research is psychoacoustic modeling. So we again took these skull whistle sounds, and we want to just compare the similarity of these skull whistle sounds to any other sound that people or humans typically experience in the environment. So we compared the similarity of the skull whistle sounds with a large collections of other sound. Just want to give a summary here. This is quite interesting. It seems like a hybrid similarity. So these skull whistle sounds are similar to animal sounds like reptiles or insects. They're also similar to other flute sounds. They're also similar to tools. What is also interesting, they're similar to environmental sounds like water rain and wind. So it seems like these skull whistle sounds seem to be really a hybrid between different sound sources. This is also what we found when we asked humans to classify the skull whistle sounds being either animated, so originating from a living object, or being more technical, or originating from nature. With the skull whistle sounds, we see it's again hybrid, so they're both classified as being animated, so originating from an animated source, or both being also from a technical source. So this is already my summary. With the skull whistle sounds, we do both computational fluid dynamics. We still work with the simplified 2D model, but in the future we want to go to these more realistic 3D models. In terms of psychoacoustic effects, I've shown you that these sounds actually sound like a hybrid, being both from an animated living nature, but also being from a technical source. Thank you very much.
All right, so the second topic, I will share the screen, and this is, we are just rushing through the topics today. So Angela just already introduced my current project, which is the Teotihuacan sound mapping project. I won't lose too many words on that. A particular branch of this project I will present today, and this is a quadruple flute research. I just put this full screen now. Here you see a 3D simulation of Teotihuacan, how that ancient city looked like in the central Mexican highlands. These instruments are quite large. The largest specimen found so far has some 63 centimeters. There are two finds which are more or less found intact. One is a bit smaller, but there were damaged parts, finger holes missing, and both instruments were restored in a way which is not up to date. Let's say it like this. When we turn to these instruments and we observe the original finds in the museums, we found one important and interesting measure, which seems to be the ground for instrument construction of this instrument, and that is a 50-50 measure taken from the second finger hole of pipe A. So in the larger instrument, and this is calculated from the edge of the window to the center of the second finger hole and then to the exit, and it's always the same measure. In the larger instrument 25-25, and in the smaller 17-5 centimeters. That is really interesting because it could demonstrate that there was some idea of instrument construction in these instruments in Teotihuacan. The larger instrument was subject to a second restoration carried out in 2004. This instrument then was enlarged, and also one of the tubes was constructed much larger than the other ones. In comparison to similar finds, fragments of Teotihuacan instruments, so we have information that this particular condition of quadruple flutes existed, but of course this is completely hypothetical, and this 50-50 measurement was not taken into consideration in this second restoration. And you see below, the smaller instrument, which is housed in another museum in Mexico City, is in a very, very poor condition. Both instruments cannot be played. Actually, the restoration carried out just made this instrument mute, unfortunately. So what we can do is only making reconstructions, and we started with manual reconstructions in clay. I worked with a instrument maker, Mexican instrument maker, in this. We went back to this 50-50 measure, so the actual reconstruction in clay is again a little bit smaller than the original, how it is exposed currently in the museum. So we adjusted the pipe length and also the fingerhole placement, and we produced I think now it's 7, 8 individual pieces with different fingerhole placements, and so we are just making experiments there. But still, the outcome of this for me was not really successive, because the instrument maker, for example, he made the finger holes all of the same size, but in the original, the finger hole sizes are individually different. What I asked Jared to do, and he will show this in his video in a minute, is on the basis of a CT scan of this reconstruction in ceramics, he took that 3D file and further adjusted it to the measurements of the original. Now, today, I wanted to show up with the print, and I ordered it in time, but unfortunately, it came out in a miniature way. It's just 7 centimeters long. And there must have been a mistake in uploading the print file. So it was just given the measures in millimeters. The thing which I received is this, and not the large instrument which I wanted to show you. But anyway, all this is like research and work in process, and there are also pitfalls. So the next time I know, okay, I have to check if actually the file which I'm uploading is given in millimeters or in centimeters. So this is my brief introduction to the quadruple flute problematic, and Jared now will show his video and his approach in reconstructing.
Hello everyone, my name is Jared Katz, and I'm the 3D research specialist for the Teotihuacan Virtual Sound Map project. I'm also a consulting curator at the Denver Art Museum, and I'm delighted to be joining you today digitally, so thank you for your attention. In this brief presentation, I will first talk about my digital methodology. I'll then provide a quick overview of the applications of this technology, and then use a case study of editing a quadruple flute from Teotihuacan. So over the course of my research, I've thus far scanned about 170 ancient Maya musical instruments, and I've now started to work with instruments from ancient Costa Rica as well. I use these models for a number of different things. I perform acoustic analyses on them, but also I make playable 3D printed replicas, which I provide to students, to Latino musicians and artists. And Latino artists and musicians throughout the US have been using these 3D prints in really interesting ways, incorporating them into their work, into their music, which is ultimately making the instruments far more accessible. For example, artist Clarissa Tosin, who's based out of Los Angeles, has been using these playable 3D prints as the soundtrack for her upcoming video piece, which is quite interesting. So when 3D modeling the instruments, this, for example, is an ancient ocarina from Costa Rica that's housed in the Denver Art Museum. And you can see the original object on the left and the 3D print on the right. So for my methodology, I tend to use photogrammetry to make the initial 3D model. Then I've worked with many damaged instruments in archaeological labs and have taken caliper measurements of the average thickness of the resonance chamber walls, of ducts. And then I use these averages to guide my digital edits of intact instruments. Then I'll print the instrument and compare the sound of the 3D print to the sound of the original object if I've been able to play it. And then we'll use that to guide future edits as well, right? Trying to get the instruments to sound as similar as possible, the 3D print to the original, that is. So this is a recording of the original object on the left. And this is a recording of the 3D print on the right. Here you can see two spectrograms. The top is of the original frog-shaped ocarina, and the bottom is of the 3D print. And you can see from the spectrogram data that the tone and pitch of the instrument are quite similar, which I was quite pleased by, right? So we can make these 3D prints sound fairly similar, almost exactly like the original objects. So I've been using these 3D prints for a number of different purposes, which I mentioned before. Over the summer and fall, I curated an exhibition called Rhythm and Ritual, Music of the Ancient Americas, which was really meant to celebrate the music played by a number of ancient cultures throughout the Americas. The last section of that exhibition included 3D printed playable replicas, which you see here. So all of these objects were included in the exhibition. And the goal was to allow people to really interact and play with these 3D prints to gain the embodied experiences of ancient musicians, right? To kind of understand what it was like to hold these objects and to play them and to hear them as you're playing them. Unfortunately, we ultimately had to stop people from interacting with them due to COVID. But the original idea was really to help people kind of gain this embodied understanding of what it was like for an ancient musician to play these objects. So now I'm going to talk about this quadruple flute in more detail. So fortunately, we had CT scan data for this object, which was amazing. So the interior ducts of this quadruple flute are identical to the original object. So the first thing I did when working with this object was I had to convert this DICOM data that we had received from the CT scan into an STL file so that I could digitally work with it and print it. So first I 3D printed a miniature version on my printer. So this is far smaller than the actual object, which is around 71 centimeters in length. So this is far smaller, but I just wanted to make sure that the STL file was intact, that it could be printed successfully, and that the ducts there were no issues with the mesh. I was then asked by the project to make a number of digital edits to this object. So first, they asked if I would scale the object. So I extended the ducts a little bit, and I also increased the width of the ducts slightly. So I used Autodesk Mesh Mixer to adjust the scaling of the instrument just a little bit to change the length and width of the ducts. I was then asked if I could block the existing finger holes and create new ones in slightly different locations that were slightly smaller in diameter. So to do that, I used Autodesk Maya. You can see here the meshes highlighted. And what I did was I used Boolean additions, basically adding plugs to block the previous finger holes, and then using that Boolean addition, embed that plug essentially into the mesh of the object. And then I used Boolean subtractions to create the new finger holes. So these new finger holes are slightly smaller in diameter, are in the side, and are in the location that the project asked me to place them. So here again, you can see how I used Boolean additions and subtractions to block the previous finger holes, add the new ones. Again, using Autodesk Maya. So in conclusion, there are many applications to 3D modeling ancient instruments, from editing to change the location of the finger hole, to 3D printing, to making these objects much more accessible to be played by students, musicians, artists. And second, the quadruple flute is just the first example of several objects that we have CT scan data for. So I'm really looking forward to working with those other objects and continuing these digital edits. Thank you very much for your attention.